Welcome back to Video Assist. The topic is projectile motion, and this topic is referenced in Unit 1, Section B, Lesson number 4, Activity 4, and more specifically the example number 2 referenced there. Make sure you've read the word problem, that's example 2 in that lesson, but it's a case of a playful student tossing a water balloon out of a dormitory window 11 meters off the ground. The water balloon leaves her hand at 6.2 meters per second, traces a parabola, and falls and strikes the ground somewhere out here. The question is, how long was it in the air, and where does it land? Well, let's go back before we start the problem. Because this is a projectile problem and because we have both horizontal and vertical components of velocity, it would be wise to calculate those components. We have a horizontal component here, we have a vertical component here, and we will calculate those. In this specific case, because the given angle was actually 10 degrees here, this value here would be 6.2 cos 10 degrees, cos because it is beside or close to the 10 degrees, and that value would be 6.11 meters per second. That means that it began at its horizontal speed of 6.1 meters per second. What about vertically? Well, that would be the sine, 6.2 sine 10 degrees. And if you work that out, that's 1.08 meters per second. Now, because the balloon starts 11 meters off the ground but ends up on the ground, we need a reference point or a reference frame to measure from. I'm going to choose the ground level to be the reference frame. You could have chosen the window level to be the d equals 0, but it would affect the equation a little bit. I'm going to go with d equals 0 at ground level. The other thing I should also define in this particular case is the direction. Which way is up and which way is positive? Is it up or is it down? In this particular case, I'm going to just consider up as positive. Again, you could have chosen down as positive. It would affect the sign of the values that you place in the equation. So let's look the time to the ground vertically. Well, vertically we often use this equation because it has the acceleration in it, and gravity does play a part and is equal to 9.8 in this particular case. So let's find out what the values are and put in the correct ones with the correct signs. Well, delta D, this is where it ends up. Well, it ends up at 0 vertically, so we'll put in a 0 here. Now, because it started 11 meters above the origin, we have to add a term of 11 meters on here. Don't forget that, because it did not start at the origin. Now V1. The V1 is the vertical velocity, and the 1.08, would that be positive or negative? It would be positive because it is upward. So we have 1.08 delta T plus 1/2. Now the acceleration. Which direction is the acceleration? Well, the acceleration is down. The 9.8 meters per second squared is always down when you're dealing with the Earth. So since it's down and up is considered positive, we have to put in a negative 9.8 here, okay, and finish and multiply that by delta T squared. If you look at that, you've got a parabola, and I'm not going to take time to solve. We have a quadratic. We're not going to take time to solve that right now, but you can check the solution that is available online. That comes to 1.61 seconds. What does that mean? It means that the water balloon will have traveled its arc in 1.61 seconds. The other question that is often asked is, where does it land? Well, that is a horizontal consideration. In other words, how far from the building did it land? How far horizontally did it land? One thing about projectiles is that the vertical motion is affected by that 9.8, but the horizontal motion remains constant. So what we can use in this particular case is the formula delta D equals the average velocity, and I'll call that the horizontal velocity in this case, times delta T. So where does it land horizontally? Well, we'll have to go back to the 6.11 meters per second. That is the horizontal velocity of the projectile, and it remains constant. That horizontal component remains constant throughout the flight. So we'll put in 6.11 times the time that we calculated for the time of flight, which is 1.61 seconds, and that works out to about 9.84 meters. That is the end of the solution that we're showing with our video assist, but make sure you also check the solution which is available at U1B4.